Before we see what happens if we fall into a black hole, we need to understand a few things. What does it mean to fall? There are two ways to look at it. We all know the story. Newton sits under a tree, an apple falls, and he wonders, why isn't the moon falling? That question led to classical physics. Newton said that all objects with mass attract each other. The more the mass, the stronger the gravity. And the closer they are, the stronger the pull. That's gravity, the invisible hand pulling everything toward everything else. We see things fall because Earth is so massive that it pulls objects toward itself. It even pulls on the moon and the sun. But why doesn't the moon fall into the Earth? Or Earth into the sun? Because they're constantly moving. They're falling, just sideways. Earth moves around the sun fast enough that it keeps missing it. Same with the moon around Earth. The centrifugal force from this motion balances the gravitational pull, creating a stable orbit. That's how satellites work, constantly falling but never hitting. Kind of like that one friend who keeps falling in love but never lands a relationship. So that's falling, according to Newton. But Einstein had something else in mind. He said things don't fall. They follow straight paths, just not in the kind of space we're used to. They move in straight lines through curved space-time. Imagine an ant walking in a straight line on a hill. The ant thinks it's walking straight, but to us, it's clearly going up or down. Space-time is the hill. The more mass an object has, the more it bends space-time. Earth doesn't orbit the sun because it's being pulled. It's simply following a straight path through curved space. We don't really feel the curve of space-time because we've lived on the same planet all our lives. Time seems to flow steadily, but that's an illusion. The curve of space-time isn't constant, it shifts with gravity. That's how gravity isn't just a force, it also warps time itself. Now let's talk about our sun. It's big. Really big. Like 99.8% of the mass in our solar system, kind of big. And with that mass comes gravity. The bigger the object, the harder it is to escape from its pull. That's called escape velocity, the speed you need to break free from an object's gravity. Now, imagine stacking suns, thousands of them. With each addition, gravity increases, and so does escape velocity. At some point, the escape velocity becomes so high that not even light can escape. That, my friends, is a black hole, a place where escape is impossible, not just for light, for anything. How does a black hole form? When a massive star uses up all its fuel, it collapses under its own gravity until it becomes a point of infinite density, called a singularity. We can't see black holes directly, but we can feel their presence. Their gravity is so strong that it bends light, distorts space, and affects the motion of nearby stars. Now, imagine falling into one. Not recommended, but hey, some people just like adventure, or have really bad GPS. As you approach a black hole, gravity increases rapidly. The difference in gravitational pull between your head and feet becomes extreme. Your feet are closer, so they're pulled harder. This stretches your body into a long noodle. That's called spaghettification, not the delicious kind, more like the sad, overcooked noodles of cosmic doom. But oh, you wanted more noodles? Fine, bring a friend. Sometimes, if two objects fall in together, gravity plays chef in a very twisted kitchen. Right near the black hole, the pair gets yanked apart. One is pulled in for the main course, while the other gets flung away with a wild new orbit. That lucky survivor can swing in much closer, grab the views, and live on to tell the tale. Astronomers actually have a name for this cosmic friendship sacrifice, the Hills mechanism. If you want me to serve that dish in full detail, comment down below. And by the way, if you were watching all this from a safe distance, you'd notice something weird. The closer your friend got to the black hole, the slower they'd seem to move. Not because they're suddenly shy, but because time itself is stretching out. Yep, black holes mess with the clock too. But let's not jump ahead. Eventually, you reach the event horizon, the point of no return, the universe's version of a do not enter sign. Think of it like cosmic bureaucracy. Once you're in, you're never getting your paperwork or your atoms back. What happens beyond the event horizon? We don't know. To someone watching from a distance, you'd appear to freeze right at the edge. You'd never seem to cross over. That's because of extreme gravity. Time near the event horizon slows down massively. That's time dilation. Your observer would die long before you even seem to move a centimeter. But you'd fall right through, toward the singularity, the heart of the black hole, a point where physics completely breaks down. Think of it like your brain during board exams. Too much pressure, zero escape, and no one really knows what's happening inside. Could black holes be portals? Some believe they might be wormholes to somewhere else. But that's just a theory. For all we know, black holes are the universe's version of a shredder, promising mystery, but mostly just chewing up everything that enters. But one mystery still burns bright. What happens to the information that falls in? According to quantum mechanics, information can't be destroyed, only transformed. Stephen Hawking suggested that black holes leak tiny amounts of radiation, Hawking radiation. Maybe that's how they slowly evaporate, returning information to the universe, somehow. Or maybe they don't. Maybe the universe has secrets it'll never share. And maybe that's why we fall, not just into gravity wells, but into curiosity, broadcasting straight from this side of the cosmos, where history, science, and curiosity collide. Subscribe for more strange truths, inconvenient questions, and topics your school never dared to explain.